Alright, today we're going to be talking about energy transfer in the atmosphere. Here are your vocab words. You have radiation, which is the transfer of energy by electromagnetic waves. Conduction, transfer of thermal energy by collisions between particles of matter. Convection is the transfer of thermal energy by movement of matter from one place to another. Stability describes whether circulating air motions will be strong or weak in the atmosphere. And temperature inversion is when a layer of cooler air is trapped by a layer of warmer air above it. Again, the vocab words, we're just getting those out of the way at the beginning. We're going to be talking about them more as we go through the slides. The first heading is going to be energy from the sun. The light from the sun travels 140 million kilometers in 8 minutes in the form of radiation. So you might want to go back and look what radiation is again, so you understand how the energy from the sun travels. 99% of the light of the energy from the sun is in the form of visible light, ultraviolet light, or infrared radiation, which we will also call IR in the future. Visible light is the light that we can see, and it is converted to thermal energy when it reaches the surface. The near visible wavelengths, so that would be infrared and UV, is what we're going to talk about next. UV waves are shorter, so they have a shorter wavelength, and that means they have more energy in a smaller space. They have enough energy to break down chemical bonds or even burn human skin, right? This would be a sunburn. They always talk about UV protection. That's why the ozone is important. Infrared waves have longer wavelengths than visible light, which means they have less energy. We sense it as thermal energy when we feel infrared. The Earth absorbs the sun's energy and then radiates it back into space or into our atmosphere as infrared radiation. So here we have the electromagnetic spectrum, with radio waves being the longest and gamma rays being the shortest wavelengths. So you can see how here they're really spread out and here they're really tight together. When they're really tight together, that means they have more energy. So visible light is right here. We have purple at the end of the side here, and red here. So when we think about this, if we hear infrared, we have red right here. So red, infrared. On the other side of that, we have violet, ultraviolet. So they're kind of giving you hints about where those land. The other part that you have to remember is that ultraviolet has more energy, and infrared has less energy. Alright, energy on Earth. Not all the sun's energy reaches Earth. Some of it is reflected back to space. Part of it that is absorbed, though, 20% of the sun's radiation is absorbed by particles in the atmosphere. So this just means if it's in the ionosphere, the thermosphere, it's speeding those molecules up. 50% of the radiation that reaches Earth, or 50% of radiation reaches the Earth and is absorbed by the Earth's surface. So that accounts for 70% of the sun's energy, and the last 30% are reflected. 25% of the sun's energy is reflected by clouds, especially if you've ever thought about it. It's always a little bit chillier on cloudy days because, I mean, it's pretty simple why. The sun's energy just isn't getting to the ground, isn't getting to us. The remaining 5% of radiation is reflected by land or sea surfaces. So, again, that makes sense. Also, ice will tend to do this. That's why it can stay cold when we have ice on the ground, because it reflects that radiation back. Radiation balance is as simple as it sounds. It's the balance between incoming and outgoing radiation. So again, make sure you know what radiation is. I keep using that word a lot. Radiation. Let's peek back. Radiation, again, transfer of energy by electromagnetic waves. And these are our electromagnetic waves. So incoming radiation is absorbed by plants, animals, land, water, right? Anything that can get heated up, that's going to absorb. Radiation is bounced back into the atmosphere as infrared radiation. This is what heats the atmosphere. And we'll see pictures of this in a second. The amount of solar energy absorbed by the Earth is equal to the amount that the Earth radiates back to space. And that would make the balance, right? We need to have one thing equal with the other. So we have incoming solar radiation here, and this is stuff that gets all the way to the atmosphere. This is being bounced by the clouds. This is being bounced by the surface. So we talked about 70% is being absorbed by the land, water, whatever it might be, plants, animals. We have 5% being bounced off the surface, 25% being reflected off clouds. And here you have the balancing part. Anything that gets absorbed over here is going to need to be let out over here. So we have infrared radiation emitted by the surface, or emitted by Earth. I'm not too worried about the different kinds of emission over here, of infrared radiation. What I really want you to understand is that these add up to 100%. This is 70, this is 5, and this is 25. Alright, so we've talked about the greenhouse effect before. A few different greenhouse gases. We talked about water vapor, CO2, which is carbon dioxide, and CH4, which is methane. Carbon dioxide gets a really, really bad rep, but the biggest one, the most important one, the one that has the most effect is actually water vapor. The atmosphere allows sunlight to pass through it, but reflects infrared radiation back to Earth. This causes a buildup of thermal energy, so this might throw off the balance, our radiation balance, and it also keeps the atmosphere warm. We've seen this before. I've drawn this on the board. If we have more of those different greenhouse gases, we're going to reflect more radiation back. So we have incoming radiation, and then the Earth wants to radiate some of that back as in the form of infrared. So it's going to, but with the greenhouse gases, with more greenhouse gases, that gets bounced back towards Earth. So we have infrared or sun's radiation coming in. We want to emit, and it gets bounced back, and we just keep following that loop back and forth, all the way across. Thermal energy transfer. Again, radiation, for what we're going to use it, is going to be transfer of energy from the sun to the Earth. And this is going to be in the form of electromagnetic waves. Conduction is when thermal energy moves from high to low temperatures. It occurs when the atmosphere touches the Earth. So we always want to, everything in Earth wants to be balanced for the most part, generally speaking. So we always want to go from high to low temperatures and balance those things out. Convection occurs when the air near the surface rises, thus transferring thermal energy to higher altitudes. This is how energy is transferred through the atmosphere. So convection is when thermal energy is transferred to higher atmosphere, or to a higher altitude. Latent heat occurs when water changes states. 7% of the Earth's surface is covered by water, thus there can be a lot of latent heat. So here we have examples. Convection is air rising, right? Warm air rising. We're going to talk about why warm air rises in a second. Radiation is the electromagnetic waves. So this is the energy given off by electromagnetic waves. And conduction is movement from a hot end to a cold end. So rising, hot to cold, and electromagnetic. Here's what we see when we talk about latent heat. We've seen this about 1,000 times now. So understand that heat is released to the environment when we're going from vapor to ice. Heat is taken from the environment, so we need to add energy or heat to go from ice to vapor. Circulating air. Low pressure on the surface leads to high temperatures. High pressures on the surface leads to low temperatures. Hot air is less dense, which creates a pressure difference. Cool air is more dense, which pushes warm air out of the way. And we'll spend some time with this, and we'll do an activity. But take a second, read back through those things. Understand what it means if something's more dense. We watched that video with the different substances, and the person performing the experiment was pouring them into a large graduated cylinder, and how they separated out very, very neatly. that had to do with density. Think about what would happen if we had something more dense on top of something less dense. So when warm air or less dense air is forced to rise, cool, more dense air sinks. So the cool air forces the warm air up. So when we say warm air rises because cool air falls because it's more dense, and things always want to be layered out like that, with the most dense thing on the bottom. In mountains, air goes up over the mountains, then back down the other side. The clouds form above mountains, rising air cools. So we know that in the troposphere, the air cools as it rises. So that's what's going to give us our circulating air. The stability is when circulating motions are weak. Unstable means motions are strong. So when we're talking about motions, we're talking about that air moving. Unstable air may lead to thunderstorms. We're not going to go into that a ton. There'll be a picture in a second. So here's what we have when we're talking about the mountains. So we have the moist air, right, and this is rising. So we would have cooler on the bottom warm air down here. As we go across the mountains, it starts to go up into the atmosphere more, so the altitude's getting higher. When it gets higher, again, the top of the troposphere is cooler than the bottom of the troposphere. So that water condenses. When that water condenses, it drops its water, right? And then here we have the rain shadow region. We don't have any liquid in the air anymore. So this is going to be dry descending air. Here we have a picture of a hail-producing thunderstorm. We have a warm updraft, cool downdraft. Right? These two things would be coming together. The cool and the warm would be meeting at a certain point, and that's what's going to make an unstable front. In this case, we have a particular kind of thundercloud, which is going to be the hail producing. I'm not too worried about how the hail is produced. What I want you to understand is that for a thunderstorm to happen, we need to have that instability. So we need to have cold downdraft here and warm updraft here, and those two things are going to kind of fight each other. Stable air and temperature inversions. Ground level air and high altitude air are the same temperature. Temperature inversion occurs when cool air is trapped by a layer of warm air above it. This holds in pollutants. So this would be what normal temperatures look like, with your warm air on the bottom, cool air, and cooler air up top. With temperature inversion, we have cool air, and then a layer of warm air, and then cool air on top of that. So we have this layer of warm air trapping the cool air on the bottom. When that happens, you can trap pollution because it doesn't move up like it normally would, and that becomes a real big issue. Alright, that does it for this set of notes.